Here we are going to start our second part of this chapter. In this chapter, we also will mention the detailed conductivity carriers of the zirconia-based electrolyte. This slide shows in the previous lecture that the zirconia will perform p-type conductive behavior at the oxygen partial pressure above the -10, and when the oxygen partial pressure reduce below than the 10, that will transform from p-type to the n-type. However, this is the most important part. When the oxygen pressure to a very low condition, is the extreme condition, then the electric conductivity will overcome the contribution from the ionic contribution. Therefore, in this region, only the ionic conductivity will transform to the electronic conductivity. Here's the two cases that we often mention for the zirconia. This zirconia, doped with calcium. Calcium has a divalent valence that quench from the 1600 or 1800. So the electronic condition of this zirconia material will perform at the 1600 and 1800. First one is the model that we proposed that it can happen for the calcium doped zirconia. When we put the calcium oxide into the zirconia, after the reaction at the 1600 or high temperature holding, then the calcium will replace the zirconia and show the two negative charged condition. And then we will have oxygen still occupied at the oxygen, but we will expel the zirconia to the interstitial site. And in this condition, the zirconia will have two positive charged condition. Or this is another condition, for the interstitial model. The calcium will also go to the interstitial condition and perform the 2+ the charging condition. Those two reactions can be explained as reactions that the cation put into the interstitial the site. The second model is an anion vacancy. It means that the oxygen will transform to the oxygen vacancies. We can write the equation like this: calcium oxide to occupy the zirconia and show the 2+ 2- the charged condition, and also form the oxygen vacancy with a 2+ charged. Based on this the equations, we may calculate the conditions that the density change with the amount of the calcium doped in the sample. And because the calcium, which is the density, which has the density different from the zirconia, so when we put in the calcium oxide into the zirconia to form the solid solution, if follow the calcium interstitial model, the density will decrease slightly. However, when we change the anion vacancy, it means the oxygen being repaired from the lattice, so the slope get more apparent for this model. So based on the calculation we have here, so we know that it's very possible that to compare the real condition. So when we measure the samples that quench from 1600, we can see this is the real data that we measured. It always follow the line like I just show here. So we know that the calcium oxygen doped zirconia follow the anion vacancy model. However, here is something more interesting and more important. When the temperature go from 1600 to 1800, and then something happened. 就像我们中国人所讲的"柳暗花明又一村"啊。The 1800, we can measure from very low doping, 10% of the calcium, to the high doping. The zirconia sample will go from the calcium institutional model gradually transform to the anion vacancy model. So this is the best part of this paper. Tell us that there are several interesting and exceptional behavior for the zirconia. And based on this, you can learn that the density, this is the very simple the data that we can measure from our sample, and also the doping the condition. Once we allow that the calcium oxide dissolve into the zirconia, forming the solid solution, then we can complete this sample, right? So don't hesitate. If you have such good idea, you should do it. This slide shows the mixed conductor that happened in the nickel oxide with multiple defects. Let me tell you that or summarize as this. The nickel oxide shows a p-type conductivity. So at the temperature, reaction temperature of interested, the hole will form, and in a higher concentration than the other defect. What type of defect we can have? In the nickel oxide case, we will have a nickel vacancy without the charge, or with one charge, or with two charged. So the conductivity at 1400 as a function of partial pressure of oxygen, just like here, the oxygen partial pressure. The diagram shows the concentration of four possible defects. Okay, then we were asked how did the defect reaction equation can be written for this. So take out your pen. I give you 30 seconds. Then you can write out the defect reaction of nickel oxide. How about the equation, defect equation that you write out in the past minutes? And let's look at this. If we have the nickel and the oxygen, try to form the hole and the vacancies. Then the first equation that we can have is here. The oxygen that come from the atmosphere, then it will go into the sample to occupy the oxygen side. However, in the meantime, the nickel will form the vacancies, okay, and also release the higher concentration of a hole. So you can see the hole here, okay, it's a highest the concentration in the condition. However, when we go to the look at the evolution of nickel vacancies, then we will have that this nickel vacancy will also in balance with the hole, so they will reduce the charge from 2 plus to the 1 plus. So you can see here's nothing, but with the 1 charge and also the 2 charge. So you can write out the subsequential the equations to describe 3 type of the nickel vacancies, and then also controlled by the concentration of those nickel vacancy, also controlled by the hole. So this is very typical cases that may happen in the nickel oxide, which is used as the anode material. But before we use it as the anode, we have to reduce it. So when we reduce the atmosphere, then we will change the oxide insulator, change the insulator to the p-type conductor. This is the potential output of the mixed conductor. We take this Syria as the example, Samarium doped Syria as the example. It's because one of our graduate students has this material at hand. We can write out the Nernst equation and also the open circuit the conditions. The Nernst equation, we put it delta phi. Okay, need to remove the effect from the electron currents. Therefore, when we have the sample, for example, an electrolyte, this is the electrolyte Syria, then the two phase, one phase where this, for example, room temperature at the normal the air atmosphere, the oxygen partial pressure in this is 0.2. However, when we go to the anode site, then we will have very low oxygen partial pressure. When we have this oxygen partial pressure condition on the two surfaces, then we will introduce a potential to drive from high partial pressure site, drive the oxygen ions to the low oxygen partial pressure site. So by using these Nernst equations, that we be able to get this value of this electrolyte. Normally it equal to the 1.1 EV at the high temperature such as 650 degrees centigrade. However, when we have a mixed conductor, we just mentioned in the previous, if the ions cannot contribute totally the electric current, then it means the rest of the contribution is coming from the electron. So we have to 1 mass E, this is electrons that we can measure it from our instrument. So 1 mass E means this is the contribution from the pure ionics. So time the theoretical values, so we can get the output, the actual value of this material. So it will equal to the theoretical output OCV, output time the T over I. This means if we allowed the Syria material here, okay, and operate in the reducing condition, therefore some of the contribution will go to the electron, and only the rest will contribute to the ionic conductivity. So the voltage output will reduce accordingly. This slide contains several very important methods to measure the ionicity, means the 离子性 of the electrolyte material. There are 4 different methods. The first method is the most reliable method and only used for the German researchers at present. Very few research groups can conduct this experiment. The experiment replaced the constant fraction of oxygen 16 by this oxygen 18 isotope. Then measure the diffusion rate of the oxygen from the air. So the material, the electrolyte, can have some of the oxygen 18, okay, after the high temperature operation. So once we can measure oxygen 18 as a function of distance from diffusion interface, then we will be able to measure the diffusivity of the oxygen ions. And the second, we can measure the electromotivated force that we just mentioned in the previous slide of the two phase of the material with electrode. The phase exposed to a different oxygen partial pressure, P1, PO1 and PO2. Then we can measure the T value, Ti and Te. After we measure Ti, Te, then we can know the amount of the ionicity of this material at the specified temperature and also the reducing the condition. The third, we can use 2-point DC method, measure the component of the electron, the current. There is no ion current because electron is more easy to diffuse. Then we can use another technique we call the EIS. It's AC impedance method for the ionic component. So we can compare those two resistance, and we can tell the details. The details will be mentioned in the chapter 12 or 13. So we can learn that in the after the midterm exam. The fourth one is the 4-point direct current method. We can see from the chapter 13. Okay, this method is we have to prepare some bar shape， 就是那个柱状的块状的这个样品。The bar shape and put 4 electrodes on the surface of this bar, and then measure the voltage and also the ions during the different partial pressure of the oxygen. Then we can tell what is the conductivity and also the electroconductivity of the materials. This is the slide showing how the driving force charge move the charged ion. When the charged ion moves, then we can measure the current. Two types of the driving force that we can get. The first driving force is by the potential. The potential, electric potential, will drive the electron or hole or the ions flow from high voltage to low voltage side. So we can measure the electric current. This driving force F over E equal to the Z. Z will be the charge number of the species, either the electron, hole, or ions. Then time the E. E is the electron 1.6 times 10 to the minus 16, 19 current, the coolant. Then this is potential, gradient of the potential. Okay, then we can write down the relationship like 5.10. The other driving force coming from the chemical driving force is mean that you have a higher concentration of oxygen. It flow from high concentration to low concentration. It also give the driving force. So the driving force from the chemical the aspect can be write down like N is Avogadro's numbers. Du dx is the chemical potential, okay, along the concentration. So we can put both together. Then the chemical potential of the two phases, okay, can be written like this. This is the potential, and also can be explained by the voltage that we applied by those two driving force, either the electric, another one is a chemical. So we put both together, okay, and the unit of this is voltage, and the current, it means the flux, okay, will drive from this. This is the voltage that we apply. If we have the gradient, we call it the strength, the voltage strength, the strength. Okay, then time the C, B, and over the NA. C will be the concentration of the diffusion species. B is mobility of this species, and then divided by the Avogadro's numbers. So we can put it at 5.14 as a combination of the two driving force. Here's the EMF of charge, the point defect for different materials. From the, for example, the diamond, silicon, germanium, cobalt, tin, and etc. Or the other interesting electronic material, such as iron oxide, titanium, this is perovskite, cobalt, ionized, or magnesium. The electromobility we just mentioned, V sub I, will go from the very high to a little bit lower, okay, or very low. Typical the mobility of the species in the oxide is low. Okay, how about the Hall mobility? Hall mobility will go from very high to very low. Here's one interesting the issues that you see. The electron or the Hall mobility for the diamond is very high, right? But why this diamond is insulator, electron insulator? Because what? Give you 5 seconds to answer this. Okay, the answer is the concentration of defects is very, very low. So the concentration is low, time the mobility, even it's high, but the total contribution to the electric conductivity, okay, is still low. Okay, this is one thing. And last thing in the last column, the point defects. The point defect that we see in the previous three, that's electron and Hall. They are the typical the semiconductive material. However, for the oxygen, the oxides, the ceramics that we use, usually then form. For example, this is the cation vacancy, cobalt. Cation means the 阳离子 the cation, the vacancies. But for the strontium titanate, it's oxygen vacancy, and etc. and etc. How about the last one? Last one is magnesium oxide, which is very similar to the nickel oxide. Nickel oxide will have what? Will have the nickel vacancies in the nickel oxide. We just discussed in the previous slide. But we also can have the magnesium vacancy, which has a reasonable mobility. Okay, for example, 3.3 times to the 6. Okay, so we can have a chemical driving force. Okay, to introduce the current that happened at high temperature. So we can say that the magnesium oxide at the room temperature is a very good insulator. But when we hit to the 1600 degrees C, this magnesium oxide can use the magnesium ions as the diffusion species, so can contribute some of the conductivities. Therefore, at the 1600, we only can say that this magnesium oxide is a semiconductive material, or we can say it's ionic conductive material. Here's several ceramic materials, okay, being identified as non-stoichiometric of the oxide. Non-stoichiometric is the oxygen to the cation ratio. It's not as what we report in our class before. For example, TiO2, okay, it's a typical the material. However, we always can have the 2 minus X. It means a little bit less in oxygen, okay, in some case, okay. In normal condition, we can say that Ti4 plus can be easily reduced Ti3 plus. So the TiO2 should be written as the 2 minus X to represent a real condition of your titanium material. Same thing for the barium titanate and the strontium titanate. Both materials are perovskite materials. The Ti is very reactive, the species, so they will give off the oxygen and reduce its charge from 4 to the 3. So those can be reduced easily. For the NiO, nickel oxide, it can be represented as 1 minus X. X range to probably to the 5 to the minus 4. Just a little bit, but still the material can be electron conductive, okay, due to this defect structure. How about cobalt? Cobalt has a similar chemical behavior as a nickel oxide. Okay, this value X can go to the 1%. Okay, how about manganese oxide? manganese oxide can go to 0.11. Okay, this 11% is a big deal. Okay, so the magnesium oxide is a very good redox material. Why redox? This means the reduction and oxidation. This means that this MnOx, the material can form either the oxidation or the reductions, the reactions. How about the iron oxide? Iron oxide can range from the 0.05 to the 0.15, 5% to the 50%. That change is ratio for the ion to the oxygens. So the anionic deficiency or cationic deficiencies may happen in the different ceramic oxides. So when we tell when we write the composition of the ceramics, we have to be very careful about the non-stoichiometric behavior of our ceramics. How about the temperature effect of the non-stoichiometry? Because the reaction, the defect reaction, were formed at a different temperature. So the most important parameter for the defect reaction are the temperature. The second is the oxygen partial pressure. So if we take the magnesium as the cases, then we can formulate the magnesium, okay, by the oxidation of the magnesium. When we have the oxidation, we will take the oxygen molecule from the air to the lattice. So the oxygen will occupy the lattice site and create magnesium vacancy in 2 plus or 2 minus the charge, and it give off 2 hole. So we can write the oxidation reaction, the rate constants, as this one. So we have the species on the right of the reaction, the equations. V magnesium vacancies times the P represent the whole, the square means the 2 times the square, then divided by the oxygen square. So we can get something like this. So Simpoliski, okay, who did this experiment in a very early time in the MIT, then determined the values with this characteristic activation energy minus 610 plus with this range, okay, then time this. So we can use this to predict the concentration of our magnesium vacancies, and also how the material that conductive at the high temperature. So let's look at those 2 cases. And then the first one is zirconia doped with the yttria. If we use yttria, which is the 3 plus valence, dope it into zirconia is a 4 plus, then we can write out the defect reaction. Please take a piece of paper and also a pen. Try yourself, okay? Do yourself to write out these reactions. Here's the equations. If we put the yttria into the zirconia, form the solid solution, the yttria will occupy zirconia and form 1 plus the defects, and then the oxygen will occupy the oxygen site, and then will form the oxygen vacancies. So we try to balance, for example, the electron, the electric balance, okay? So we have, here's a -1, here's a +2, so we have 2 times. And also the mass balance, we have 2 yttria here and the 3 oxygen here. Here's the vacancy, nothing here. And how about the site? So we have a 2 zirconia site and also 4 oxygen site. So we keep the 3 things all balanced. How about the second case? the Syria doped with niobium. Niobium is 5+ balanced. So we can write the equation. Try yourself. Okay, write down the equations. Okay, so we can look at this. The niobium with the 5+. So when it occupies the Syria site, then we can have, for example, the one charge, 1 + 1, the valence. Okay, if you have a 2 niobium on the left, so you can have 2 over here. Okay, however, when we have a 2 charge on the right, positive charge, so we have the something on the left. So we have 1 oxygen vacancy with a charge, 2 positive charge. So we can also find how many the site that you can have for the Syria. Okay, here we have 2 Syria, okay, and also 5 oxygen site. But on the left, you have oxygen site available here. So you still keep the site for Syria and oxygen 1 to 2. So do you finish this correctly? So you have to write this defect equation as fluent as possible, so you can deal with the questions that we might have in your midterm exam. Here is the different kinds of the ionic carriers. Okay, based on the different structures and also the compositions, the dopants, then the carrier will change from one to the other. Most of the cases that for the oxides, the carrier is the oxygen ions. However, for some type of the crystal structure, we call it aurelius structures. Aurelius structure is a layered structure that happened or found very often to the sodium aluminate or alumina-based materials. That these materials will have sodium between the layers. The layers consist of alumina. Okay, so the sodium ion can diffuse through the layers. Same thing for the beta alumina, okay, which also have some amount of the sodium inside, and also the potassium as well. So we say it is alkali ions. That means that including the sodium and the potassium, 就是钾了哈, and other the small ions. How about the lithium glass? That will allow the lithium diffuse through the glass. So the lithium ion, okay, is a major carriers for these materials. How about the effect of the temperature? We can write the dependence of the conductivity, okay, to the temperature. Over here, this is Arrhenius equation that we write this especially for the electric conductivity. So we note the constant, the terms sigma 0 needed divided by the temperature T. Okay. So how about the activation energy of this process? We can measure it from the different the data. So in the first slide of this chapter, we know that basically the electric conductivity as a function of the temperature can have 4 different types of the dependence. Let me give you the several the dependence, the cases that we can read from this. The potassium or sodium diffuse in the layer, the beta alumina, we just mentioned in the previous slide. The activation energy is 0.5 eV. That show the almost a straight line from room temperature is here, to the about 400 degrees over here. Show a single diffusion mechanism that controlled by the potassium or sodium, the species diffusion. How about the second case here? Second case show the yttrium doped zirconia show the B-type behavior. B-type here, okay? They show the two slope, the dependence. The first slope, okay, is a little bit higher in the activation energy here, 0.96 eV, and another one is 0.92 eV. Okay. Also, we have reported several years ago that also can be 93 or 89 kJ per mole. This is different units. So the value, okay, show a little bit different. In this case, we learned that for the conductivity at a lower the temperature region, okay, the difference from the mechanism that controlled at a higher temperature. So we have to realize that the turn point over here, okay, on the diagram, turn point will determine which type of defect, okay, control the electronic diffusion. The case 3 is the not the Samarian doped Syria, is a gadolinium doped Syria. This one, gadolinium, also show the 3+ valence, okay, with the average grain size of 0.29. If increase from very small the grain size, increase the grain size to 5.6, then the activation energy reduced from 83 to the 79 due to the change of the control mechanism. When we increase the grain size, normally we will reduce the effect coming from the grain boundary, so the activation energy change accordingly. Due to the effect of the grain boundary phase, okay, this is the grain boundaries is non-conductive. So what we will have a behavior similar to the C like this one. At a lower temperature, okay, that it means that it will interact or interrupt by the grain boundary. However, at the high temperature, the grain boundary effect is diminished, 就是减少了哦，就是来自经界的这些影响因素会减少。Therefore, the conductivity, okay, improved. So based on the 3 cases that we have, okay, we know that the oxide material will perform differently. How about the redox reaction we just mentioned in the previous the slide? The oxygen and reduction reactions, okay, it happened depending on the different oxygen partial pressure. For the oxidation reaction, okay, we can write the 2 type of the reaction like this. The oxidation, we will take the gas oxygen molecule from the gas, and it will go to the sample. This is the oxygen vacancy in the sample, and also take the electron from the samples. Then we can diminish the oxygen vapors, oxygen vacancies, and to show the equation like this. Or we can write the second one. For example, we take the electron, okay, to other side of this equation, okay. So we will write out a similar equation, okay, as the previous one. So the rate constant for the first, the one is K sub O. O means the oxidation, equal to the PO2 square, and then the oxygen vacancy and N square, etc. How about the reverse reaction to the oxidation? We call it reduction or reduction. Reduction means the reaction will go to the left-hand side, Okay, so the reduction, okay, will have the reaction constant will have just reverse of the 5.21 like this. Here's the flower diagrams that we normally to describe the concentration of defects as a function of oxygen partial pressure at specified temperature. 布劳尔这个图啊，是一个非常重要的图哦。我们在这边呢，我们不只要用英文讲一次，我们会用中文再告诉各位一次。 在这边呢，各位可以看到各种不同可能发生的这个defect， 包括电子啦、电动啦，还有它的刚才讲的反应式啦，或者说不同的一的是阳离子或者阴离子的这个vacancy 的浓度等等，我们都可以在这张图上面利用这个缺陷浓度跟氧分压之间的关系，在特定的温度之下，我们都可以让它表示出来。所以在这个地方呢，我们呢把那个先讲一点点然后我们会在下一个休息完了之后，在下一个时间呢，再告诉各位这一个整个图的物理意义是怎么样。那在这个图里面，因为氧分压它有分区域，那它有分高的氧分压、中的氧分压跟低的氧分压的这个部分。那高氧分压的，比如说在右手边这边，那高氧分压的时候，平常都会让我们产生 P type 的这个样品。那在中性的这个地方，就在这个地方，我们现在画一条当量中性的这个地方。到这个地方呢，我们的电子跟电动呢会达到平衡。那这个时候的defect呢会最高，然后再来到低氧分压的这个地方呢，它刚好完全会相反。那这个时候呢，它的整个图形呢就会出来。好，那我们在这个地方呢休息个10分钟呢，我们再继续我们的后续的这个讲课。